Okay, so here's where we were yesterday. We were looking at this function, f of x. We did a lot of work on this. We calculated the first derivative. We found the critical numbers were at 0 and 1, right? By applying the zero product property when we got this thing all factored. And there it is in yellow, right? There's the factored version of that derivative, okay? And we calculated the second derivative, and we were just in the process. I think we just finished up the second derivative, right? We knew that this was our second derivative in factored form, what I'm pointing at right there. To find the zeros, we know that by the zero product property, the zeros of the second derivative would be the zeros of the factors of the second derivative. The first factor has no zeros, right? That exponential function never crosses the x-axis, never touches the x-axis. But this quadratic might. So we just applied the quadratic formula, and we found that we got the two solutions, 1 plus or minus the square root of 2 over 2. Right. So now what we have to do is we're just going to take all this information and we want to build our table from it. Okay. So let's build our table. Okay, real quick, our critical numbers. You guys just remember, somebody write these down. So the first derivative, they were 0 and 1. And for the second derivative, it was 1 plus or minus the square root of 2 over 2. So write those down. I'm going to go to the next page, and I'm going to need those. And our domain, we decided, remember, was all reals. Okay. And maybe I need to take a quick picture of the first derivative, because we're going to need that. And our second derivative. Okay. There we go. So there's our domain. The first derivative critical numbers were 0 and 1, correct? Wasn't that right? Give me a thumbs up. Is that right? Okay, second derivative was 1 plus or minus the square root of 2 over 2. So that's going to be, up there somewhere, 2.2414, something like that. So then down here, we're going to get a negative value, 1 minus square root of 2 over 2. If I want to put in rough approximations, that's approximately 2.414, and this would be something like approximately negative 0.414, I believe. So they're just to give us an idea what kind of test values we want to pick. So now what? I guess we can, what am I going to put in my second derivative row here?
The second derivative is going to be 0 at 1 minus square root of 2 and 1 plus.
The second derivative. Okay, so we can do that. We know the second derivative is 0 there and there. Good. How about the first derivative row?
It's going to be 0 at 0 and 1.
Okay, so I get zeros there. Remember, those are critical numbers, aren't they? And then what does that tell me when I want to draw my little icon at the bottom? What do I know if I have zeros of the first derivative at these x values? I want to represent what these critical numbers are, right? What piece of the puzzle does that provide? Go ahead, Seth, again. Not asymptotes, horizontal tangent. There we go. Good. We got horizontal tangents to our curve right there. Okay, good. All right. What do we suggest next here? Let's see. Somebody different. I'll throw it out for just, you guys can kind of just contribute on your own here. Or if not, I'll just ask questions. But somebody else pitch in. What's the next step? Just talk me through this. We got to just kind of just spend a little time talking through this process. That's taking too long. Natalie, help us out. Uh-oh, Natalie froze. Say, you froze there for a second. Say it again, Natalie. Oh, okay. Natalie's having some connection problems. I'm skipping Natalie. She probably had the right answer there, but I can't hear it. Let's see. How about Miss House? What are we doing next here? Perfect. We'll use the second derivative test. Good. So we'll evaluate the sign of the second derivative at our critical numbers. Good. So here's our second derivative. So we get f double prime of 0. Okay, that's an easy one, isn't it? That's going to give us, what is e to the 0? Everybody, show me, hold up fingers. What's e to the 0? 1. Good. Anything to the 0. Anything other than 0 to the 0 is 1, isn't it? So I'm going to get positive times, what am I going to get over here? 0 minus 0 plus 1. So I get a positive times 1. So it's positive, isn't it? So what's that tell us is going on at that critical number, Daisy? What's happening at 0 if it's a 0 of the first derivative and has a positive value of the second derivative?
Is it like what the graph strings are?
Exactly. Yeah. What's going on there? What kind of what's the graph doing there?
Is it concave up?
Right. So what's that make this then? A maximum or a minimum?
A minimum.
Good. And remember our little trick. A positive function is a happy function, right? Positive second derivative is a happy function, so it's smiling. Concave up, minimum. How about at 1? F double prime of 1 is going to give us 2 times e to the any power is positive, isn't it? Right? Everybody agree? The exponential function is always above the x-axis. If I plug 1 in there, I get e to the negative 2. That's just 1 over e squared. That's positive, right? E is a positive constant. So I'm getting positive times 2 minus 4 is negative 2 plus 1 is negative, isn't it? So positive times negative is negative. So we know that's concave down, and that makes it a maximum. Okay? What happened here? Something's goofy. Something's goofy here. Hang on. Something is really goofy. What is going on? Oh, you know what I did? I see what's going on. I put these. Oh, it's 1 over the square root of 2. Yeah, no wonder. Okay, so these are wrong. These are wrong values. I put these in the wrong places. This is like going to be, that's like 1.7. Now I was treating that like a square root of 2, not 1 over the square root of 2. So, yeah. That's what that was, right? It's like, put that in your calculator real quick. I like 1.71-ish. And this would be something like, it should be in here. That's like 0.29-ish. Is that right? Okay.
That's about right.
Okay. Okay, so I just got to transfer all this stuff over there. No wonder. Did you see what my problem was with that? Why I knew that couldn't be possible? Can anybody tell me why I looked at that and said there's no way that's right? This is a good question.
Because there were inflection points on either side of the maximum value.
Well, potentially.
In between.
Okay, yeah, I needed one in between, didn't I? Right? Because look what's going on in the middle. I've got a positive concavity here and a negative concavity here, and my second derivative is defined everywhere, right? So there's no way that we could have had that switch in concavities without there being an inflection point in the middle, right? See what I'm saying? The derivative was defined everywhere. The functions, there's no sharp corners on this thing, so that couldn't have happened, right? So that told me that is not possible. Okay, so here we have, that's supposed to go there, and yeah, there we go. Good. Now I think we're good. Okay, so look, we did two things at once here, right? By applying the second derivative test, we found those concavities, and we also determined that this 0 of the second derivative is an inflection point. Okay, what else do we need to do, though? One other thing we got to do here. You see anything else, Andrew, we got to do? We left one unanswered question.
I don't know.
Kirsten, you got an idea?
Is it just that we haven't figured out what the last set of points is?
Yes, good, right? We haven't figured out, we've got this, we've got a 0 of our second derivative here, but we need to know if that's a point of transition of the second derivative, don't we? Because that's a potential inflection point, and we're supposed to find the inflection points. Right, so we need to pick a test value up here to the right of this 0, don't we? And just see what the sign of the second derivative is. Okay, so let's try that. So something bigger than that would be like, I don't know, let's just pick 5. So if I evaluate my second derivative at 5, what are we going to get? If I plug 5 in, I'm going to get positive there. I'm going to get 2 times 5 squared is 50 minus 20. That's obviously going to be positive, isn't it? That's pretty big. That first term is pretty big. So I get a positive result. So yeah, I can see that this is also an inflection point, isn't it? Okay. And if we wanted to go back and plug in some values for x into the function, we could turn these into points if we wanted to. Do we really want to do that? Probably not. I mean, you ever get that? I could plug these x values in up here and these x values in up here, and I could turn these into points, right? If I turn these into points, that allows me to make a more precise graph, right? But let's not worry about that. That's just extra time. We know the important stuff. We know maybe all we needed to know is what are the X values where we have minima and maxima and inflection points. And we found those, okay? What's our graph look like? Rather than us taking the time to plug those in, let's just cheat and look at the graph. Okay, does that match up with our graph? Yeah, it matches up pretty well, doesn't it? Right, at 0, we've got a minimum, okay? Concave up at about 0.29-ish, right? At the 1 minus the square root of 2 over 2, we've got an inflection point where we're changing from concave up to concave down. We've got a maximum at 1. It's not a very dramatic maximum, but that is a maximum, right? And then out here at 1 plus square root of 2 over 2, or about 1.71-ish, we've got another inflection point where we change from concave up back to concave down, or other way around, concave down to concave up. Okay. Maybe there's one other thing we could do here that we could add to this that might be sort of useful. So what if we take limits on this? Well, okay. Yeah. Do we even need to? Can you tell me, these are kind of interesting questions. Ponder this for a second. If I take the limit of f of x as x approaches negative infinity, can you tell me what the answer has to be? And you can look at this a number of ways.
Shouldn't it tend towards positive infinity on both sides?
Okay, let's take the left side first here.
So positive infinity?
Okay, how come?
Because, well, the plus 5 won't end up mattering, and then the x squared is going to tend towards infinity because it's x squared, and then the e to the negative 2x, that'll be just multiplying it by e to some positive infinity number.
Okay, so
it'll be negative 2 times negative infinity.
Okay, so let me paraphrase. That's good. So one way we could do this is we could look at the behavior of the function, right? We know that leading term is going to dominate. As x approaches negative infinity, we're going to end up with a huge negative number squared, which gives me a huge positive number. So that's going to look like a positive infinity-ish number, right? Times e to the negative 2x. Well, e to the negative 2 times negative infinity looks like e to the infinity, also a huge positive number. A huge positive times a huge positive is a huge positive. The other way we could have looked at it is that if this is concave up everywhere here, then what is this thing going to do? I mean, it's got to be tailing up to infinity, doesn't it? Because it's coming out of a minimum and it's tailing up forever. Okay, does that make sense? We got a place where we know that because we could fill in some blanks here. Let me say this a different way. Because this is a minimum, and here's our first derivative critical number, right? We know, would everybody agree that we could surmise from that, right? Because it's a minimum, to the left of that critical number, that the function has to be decreasing, and so the slope has to be negative. To the right, the slope has to be positive, right? Because it's increasing. Okay? So if we've got a positive concavity and a negative first derivative, that means that this thing has to be going up forever, right? It has to be going up. In fact, it's going to go up at an accelerated rate. It can't do something like if here's the minimum, it can't do something like that because there'd have to be another inflection point there, right? If the concavity is always positive and the function is decreasing, that means it's bowl-shaped up and we're getting steeper and steeper slopes the further we go to the left. Anybody see that? That's kind of it's hard to see that at first, but once you get practiced at this, it's really not a big deal. I mean, that's kind of the connection you want to practice making when you're doing all this stuff, is you want to, in the back of your mind, you always want to try to connect what the tables are telling you and what the function looks like with what a sketch of the graph would be, right? To make that, and we've done a lot of practice on that. We'll continue to, right? To make those connections between what it means to have, positive or negative first and second derivatives, what that implies about what the graph has to look like. That's really valuable stuff to get good at, okay? What about the right side? Okay, so Seth, you were suggesting it has to go up to infinity at the right side. Anybody, want to change that?
Well, it looked like that, but now I'm thinking probably differently.
Okay.
I don't know.
Okay, well, let's look at this analytically first here for a second. Let's just look at the table, right? If we look at our table, we know this is a maximum here, right? So to the right of x equals 1, the first derivative has to be negative, okay? Everybody agree? If we've got a negative first derivative and a positive second derivative, what does that tell us? We've got a decreasing function that's concave up, right? What in the world? What does that look like? If it's a decreasing function that's concave up, doesn't that have to amount to something like that? Everybody agree? Right? That's kind of a probably hurts your brain to think about that a little bit, but you see where it has to be that way? There's no other way that we could do that. We're going to have a decreasing function. It decreases all the way to infinity, and it's concave up all the way to infinity, right? So this thing has to be asymptotic somewhere, doesn't it? Right? See what I'm saying? Okay. Let's see. I want to think about that myself for a second. Okay, I don't know if I'm comfortable with that one because it seems like maybe it could decrease and not be asymptotic. Okay, so we're going to abandon that. I'm not sure if I buy that. That doesn't seem quite right to me. But let's just look at the behavior of the function, right? We can always just go back and take a limit. If we take the limit of this function, the first term is going to dominate, obviously, right? So what's going on with the first term as x approaches negative infinity, okay? So let's rewrite this. The e to the negative 2x, let's rewrite that as e to the 1 over 2x. 1 over e to the 2x, sorry. So we're taking the limit of x squared over e to the 2x as x approaches infinity plus 5, right? Okay. What's that term going to do? The top and the bottom of that function both approach infinity, don't they? Right? Everybody agree?
Is this a slant asymptote?
No? Mm-mm. The top and the bottom both approach infinity. If I let x go to infinity, that first term is going to be infinity over infinity, right? Okay, so that's indeterminate. Can you make a guess here as to which one's going to win?
The e to the negative 2x.
Okay, how come, Andy?
Well, like before you put it in fractional form, x squared when it's approaching infinity is infinity, but e to the negative 2 times infinity just becomes so small, it becomes 0 pretty much, and so 0 times infinity is 0 plus 5, so it asymptotes at 5.
Well, okay, 0 times infinity is still indeterminate. Okay. So you can't say, there's a whole slew of indeterminate forms that we're going to practice with here in the near future. But let's see, where do I have a little room? This page, I can get rid of this thing. I don't need this anymore. These are all indeterminate forms. meaning more work, right? If we take limits and we get these results, well, we've already talked about like 0 over 0 was the first one we looked at, right? Another one would be infinity over infinity. We don't know. Could be anything. 0 times infinity doesn't work. Okay, those are all examples, and there are others, but those are the ones that probably make sense right now. How do you know what 0 times infinity is? Because this isn't truly 0 and this isn't truly infinity. This is a value that's approaching 0, and that's a value that's approaching infinity. So really it just depends on which one is doing that more aggressively. Is this first factor approaching 0 more aggressively than this factor is approaching infinity, or vice versa, right? So this is still indeterminate. We could still probably reason through this, though. Think about the behavior of these graphs. An x squared graph compared to an exponential graph. Which one grows more aggressively as x gets big?
The exponential.
Yeah, the exponential function does, doesn't it? And you know, this probably isn't a very satisfying argument, because it's, you know, there's nothing very concrete about it. But let's just graph these two and just show you real quick, side by side. If I take any power function, it could be x to the x squared or x to the 9 billion. It doesn't matter. They're going to grow at a rate that is, they're going to get really big really fast for sure. They're aggressive functions, but they're going to grow differently than an exponential function. So let's take f of x equals x squared. And then next to that, let's take e to the 2x. It's not even close, right? After a while, you're going to see that, you know, like if I, let me make this y-axis really big. Right? I mean, it's not even close. That exponential function, after a while, just is always going to dwarf the power function. And it makes sense, doesn't it? Because the exponent is what's increasing, and you get a lot more traction out of increasing an exponent. Oh, you guys couldn't even see that, darn it. There you go. There it is, right? There's the parabola. There's the exponential function if I skew the x and y axes a little bit, right? Exponential function just dominates, okay? How come? Because, you know, it makes sense, doesn't it? If the exponent is what is growing, an exponent gives you more traction to grow a function than the base does, right? 2 to the 4th, or let's say 2 to the 10th is a lot bigger than 10 to the 2nd. Agreed? Okay. All right, I'm going to show you something else here, because this just seems like this is a little out of sequence, but I want to show you another great trick. Super easy, but really effective. Okay, this is called L'Hopital's rule. And I wasn't planning to show you this today, but it just seems like it fits so well today. We'll come back and I'm not going to give you any assignments on this yet. We'll come back and review this, and I'll give you an assignment. That's a capital L. It's a French name. What L'Hopital's rule says is that if you have an indeterminate form in one of these two forms, then you can differentiate this thing repeatedly, the top and the bottom, until it's no longer indeterminate, and that resolves the indeterminacy. That's pretty slick. That would have been useful at the beginning of the year, wouldn't it? Right? For example, let's take a really simple one. If I end up with the limit of f of x equals, let's just say it equals x squared over x. That's the function that we get as x approaches 0. That's indeterminate, right? Everybody agree? That gives me 0 over 0, so it's indeterminate. Everybody buy that? Give me a thumbs up. Okay. Well, by L'Hopital's rule, the limit of f of x, if the limit of f of x as x approaches 0 is x squared over x, it's also equal to the derivative of the top, which is 2x over 1. Next x approaches 0, what do we get? Well, we're getting 0, aren't we? Right? Indeterminacy resolved, right? Okay, what if we have something like this current example? What if we have something like the limit of just this term right here, x squared over e to the 2x? Let's just take that one little part right there. Where's my, there it is. And we'll come back to this. We'll come back and spend a lot more time on this, but it just fits, it solves our problem for today. So I want to show you a way that we can easily answer what the limit has to be on the right side. So that's indeterminate. I could take the derivatives of the top and the bottom here, right? And this equals the limit of the derivative of the top is 2x. The derivative of the bottom, would everybody agree, is just 2e to the 2x, right? Still indeterminate, but I can differentiate again. Derivative of the top is 2. Derivative of the bottom is 4e to the 2x. That's not indeterminate anymore, is it? Right? Now I'm getting an answer where I have 0 over infinity, which is 0. Everybody good with that? You may not be totally good with that, but we'll come back to it. But that's just a great application of L'Hopital's rule. So that allows us then to get this graph, doesn't it? All right. So this thing has, if I take this limit, this term right here, we just evaluated the limit of this term, and it went to 0. And so our answer is just 5. And we can see on the graph that there's a horizontal asymptote here along the line x equals 5. Okay? All right. You know, sometimes we just never know where our little calculus journey is going to take us. Took us on a little detour today, but that was a pretty cool detour. All right, let's look at another one. See if we can maybe get through at least most of this problem today, and then we'll start rational stuff next time, rational functions. Okay, so we'll kind of zip through this. What is our domain? Ponder that for a second and tell me what the domain is. Why don't you type it in chat, what you think the domain is. And if you're just taking an educated guess, just put a question mark by it, and you can still put an answer in. Any other answers? Everybody weigh in on this real quick. What do you think? Okay, Caleb and Amber, you're right. Amber, how come?
I don't think you can have a natural log of a negative.
You're right. That's why, right? Because we've got a natural log there. Look at this. What parts, where do we have red flags on this function for the domain? Not there. That's fine. Negative 2x squared, there's no value of x. You can't input. 19x squared, no value. But right there is a red flag, right? There's a factor in that first term of log x. And so there we drop a red flag. We know that the log function We reviewed this the other day, right? A log function just looks like this. That's a log function, right? Could be any, they're all going to cross at the point 1, 0. Okay, and any base log is going to look essentially like that. If I pick, this is a base E log, if it's a base 10 log, it's going to be the same shape, slightly distended, but that's what they all look like, right? So what's the domain of a log function? Well, right? And we have a log function here, and so our domain is x is greater than 0, right? So there's our domain. Okay? Let's take some derivatives then. First derivative. So we got a product rule, don't we? We've got negative 2x squared times the derivative of log x. What's the derivative of log x? Johan?
1 over x.
1 over x, good. Okay, plus log x times the derivative of negative 2x squared. Well, that's just going to be, what, negative 4x. Plus the derivative of this other term, which is just 38x. So we could combine some like terms here. Look, there's a little cancellation. I get the x's canceling top and bottom there. And so I get a negative 2x plus 38x is 36x minus 4x log x, right? So there's my first derivative. Okay, what about my second derivative? So I'm getting 36 minus whatever I get from that product. So 4x times the derivative of log x, which we just were reminded is 1 over x, plus log x times the derivative of 4x, which is 4. And I put my negative sign there, right? So we're subtracting the product. Okay? And if I simplify that, what do I get? So these cancel, the x's cancel. So I get 36 minus 4 is 32 minus 4 log x. Okay, give me thumbs up if that looks right to you. Okay, nobody sees any errors. Okay, I got the thumbs up there from one person, so I feel like I must be okay. Somebody was checking my work, which you obviously got to do, I've been known to make some mistakes. So if I factor the first derivative, I could factor out a 4x, right? And that leaves me with 9 minus log x. Second derivative, if I factor that, there's really not much use in factoring that. I'm just factoring out a constant. We'll just leave it the way it is. So where are the derivatives of the first derivative then? Or sorry, the zeros of the first derivative. In our domain, the first derivative is defined everywhere, right? Our domain from 0 to infinity. Where does it equal 0? What's one place where it equals 0? Isaac, what's one x value where our first derivative is 0? Here's our first derivative, right?
I forget what. And x. I get them mixed up a little bit.
Okay, so you can forget about this one then, but what about this factor right there? What's the 0 of 4x?
0.
Okay, so 1 is going to be at x equals 0.
I was looking at the second one, sorry.
Okay, that's fine. In the second one, let's look at that one. So the second one would be 0 when log x equals 9, right? Everybody agree? Okay. So how do I solve that? How do I solve that log equation?
You do e to the power ln x.
Yeah.
And you do it to the side.
Good. I'll just exponentiate both sides, right? So I'm just going to do e to the log x equals e to the 9, and e to the log x is just x, isn't it? So we get two critical numbers. We get x equals 0, and we get x equals e to the 9th, which is just a number, okay? Two critical numbers. What about the second derivative? Are there any values there where that's equal to 0? Well, we can find out. Let's set it equal to 0 in C. So we know f double prime equals 0 when 4 log x, if I set that whole thing equal to 0, when 4 log x equals 32. In other words, when log x equals 8, right? Okay. So then we could do the same thing, and we get the critical number x equals e to the 8. Okay, big number. Okay, anybody with me? All right, so let's make a table then. I'm going to steal my table from there. So our domain this time is from 0 to infinity. We had first derivative critical numbers at 0. Is that a legit critical number then? Thumbs up or thumbs down? Only getting one person weighing in on that. Is 0 a legit critical number? Yes or no? Thumbs up, thumbs down. Okay, now I'm starting to get more votes here. Yeah, it's thumbs down, isn't it? Good. Oh, there. Okay, good. Everyone was joining the party here. Yeah, so it's thumbs down because it's not in our domain. We can only have critical numbers that are in our domain, right? And that's not in our domain. So we can cross this guy out. It's not even, that one doesn't mean anything, okay? But we get a second derivative critical, we get a 0 of the second derivative at e to the 8th, and we get a critical number at e to the 9th. So this is going to be a little bit goofy here. I mean, e to the 8th is a really big number, so this is going to be not necessarily like a linear. We're just going to put these on here somewhere, and it may not be proportional. There's e to the 8. Here's e to the 9. E to the 9 is a first derivative 0. E to the 8 is a second derivative 0. So what should we do next? What do we want to do to analyze this thing here? Madeline.
Don't you plug in e to the 9th into the second derivative
Okay.
equation?
Yeah, good. Let's take e to the 9th and plug that in. And what do we get? If I plug e to the 9th into my second derivative, there's my second derivative. So second derivative evaluated at e to the 9th would be 32 minus 4 times the natural log of e to the 9th. What's the natural log of e to the 9th, everybody? Hold up fingers. If I take the natural log, there you go, good. It just cancels the exponential and the log cancel, and I get 9. Good. So I end up with 32 minus 4 times 9 is negative something, right? Negative 4. Okay, so that's negative. And so look, we know that this is then a maximum, right? Oh boy, we're out of time. Okay, carry on. I'm going to put up the first assignment covering just this continuation of this stuff so you can be working on it. And we'll just wrap this up, and hopefully we'll get through like 2 rational functions next time. And then we're getting close to being done with this section. But there's still a few more things I want to cover, okay? All right, have a great weekend. I am here after school if you need me for anything. Otherwise, I'll see you on Tuesday.